In electric power generation, a combined cycle is an assembly of heat engines that work in tandem from the same source of heat, converting it into mechanical energy, which in turn usually drives electrical generators. The principle is that after completing its cycle, the working fluid of the first heat engine is still low enough in its entropy that a second subsequent heat engine may extract energy from the waste heat of the working fluid of the first engine. By combining these multiple streams of work upon a single mechanical shaft turning an electric generator, the overall net efficiency of the system may be increased by 50 to 60%. That is, from an overall efficiency of say 34% to possibly an overall efficiency of 51% in net Carnot thermodynamic efficiency. This can be done because heat engines are only able to use a portion of the energy the fuel generates. In an ordinary heat engine, the remaining heat from combustion is generally wasted. Combining two or more thermodynamic cycles results in improved overall efficiency, reducing fuel costs. In stationary power plants, a widely used combination is a gas turbine burning natural gas, a synthesis gas from coal, whose hot exhaust powers a steam power plant. This is called a combined cycle gas turbine plant, and can achieve a best-of-class real thermal efficiency of around 54% in baseload operation, in contrast to a single-cycle steam power plant which is limited to efficiencies of around 35 to 42%. Many new gas power plants in North America and Europe are of the combined cycle gas turbine type. Such an arrangement is also used for marine propulsion, and is called the combined gas and steam plant. Multiple-stage turbine or steam cycles are also common. Other historically successful combined cycles have used hot cycles with mercury vapor turbines. Magnetohydrodynamic generators are molten carbonate fuel cells, with steam plants for the low-temperature bottoming cycle. Bottoming cycles operating from a steam condenser's heat exhaust are theoretically possible, but uneconomical because of the very large, expensive equipment needed to extract energy from the small temperature differences between condensing steam and outside air or water. However, it is common in cold climates to drive community heating systems from a power plant's condenser heat. Such cogeneration systems can yield theoretical efficiencies above 95%. In automotive and aeronautical engines, turbines have been driven from the exhausts of Otto and diesel cycles. These are called turbo-compound engines. Basic combined cycle. The thermodynamic cycle of the basic combined cycle consists of two power plant cycles. One is the Joule-Brayton cycle, which is a gas turbine cycle, and the other is Rankine cycle, which is a steam turbine cycle. The cycle 1, 2, 3, 4, 1, which is the gas turbine power plant cycle, is the topping cycle. It depicts the heat and work transfer process taking place in high-temperature region. The cycle ABCDEF, which is the Rankine steam cycle, takes place at a low temperature and is known as the bottoming cycle. Transfer of heat energy from high-temperature exhaust gas to water and steam takes place by a waste heat recovery boiler in the bottoming cycle. During the constant pressure process 4:1, the exhaust gases in the gas turbine reject heat. The feed water, wet and superheated steam absorbs some of this heat in the process A, B, C in CD. Steam generators. The steam power plant gets its input heat from the high-temperature exhaust gases from gas turbine power plant. The steam generated thus can be used to drive steam turbine. The waste heat recovery boiler has three sections: economizer, evaporator and superheater. Design principle. The efficiency of a heat engine, the fraction of input heat energy that can be converted to useful work, is limited by the temperature difference between the heat entering the engine and the exhaust heat leaving the engine. In a thermal power station, water is the working medium. High-pressure steam requires strong, bulky components. High temperatures require expensive alloys made from nickel or cobalt, rather than inexpensive steel. These alloys limit practical steam temperatures to 655 degrees Celsius, while the lower temperature of a steam plant is fixed by the temperature of the cooling water. With these limits, a steam plant has a fixed upper efficiency of 35% to 42%. An open-circuit gas turbine cycle has a compressor, a combustor and a turbine. For gas turbines, the amount of metal that must withstand the high temperatures and pressures is small, and lower quantities of expensive materials can be used. In this type of cycle, the input temperature to the turbine is relatively high. The output temperature of the flue gas is also high. This is therefore high enough to provide heat for a second cycle which uses steam as the working fluid. In a combined cycle power plant, the heat of the gas turbine's exhaust is used to generate steam by passing it through a heat recovery steam generator with a live steam temperature between 420 and 580 degrees Celsius. The condenser of the Rankine cycle is usually cooled by water from a lake, river, sea or cooling towers. This temperature can be as low as 15 degrees Celsius. Typical size of CCGT plants. For large-scale power generation, a typical set would be a 270 MW primary gas turbine coupled to a 130 MW secondary steam turbine, giving a total output of 400 MW. A typical power station might consist of between 1 and 6 such sets. Plant size is important in the cost of the plant. The larger plant sizes benefit from economies of scale and improved efficiency. Gas turbines of about 150 MW size are already in operation, manufactured by at least 4 separate groups: General Electric and its licensees, Alstom, Siemens, and Westinghouse, Mitsubishi. These groups are also developing, testing and/or marketing gas turbine sizes of about 200 MW. Combined cycle units are made up of one or more such gas turbines, each with the waste heat steam generator arranged to supply steam to a single steam turbine, thus forming a combined cycle block unit. Typical combined cycle block sizes offered by 3 major manufacturers are roughly in the range of 50 MW to 500 MW and costs are about $600 per kW. Unfired boiler. The heat recovery boiler is item 5 in the COGS figure shown above. No combustion of fuel means that there is no need of a fuel handling plant, and it is simply a heat exchanger. Exhaust enters in superheater and the evaporator and then into economizer section as it flows out from the boiler. Feed water comes in through the economizer and then exits after having attained saturation temp in the water steam circuit. Finally, it then flows through evaporator and superheater. If the temperature of the gases entering the heat recovery boiler is high, then the temperature of the exiting gases is also high. Dual pressure boiler. It is often desirable if high heat is recovered from the exiting gases. Hence, dual pressure boiler is employed for this purpose. It has 2 water steam drums. Low pressure drum is connected to low pressure economizer or evaporator. The low pressure steam is generated in low temperature zone. The low pressure steam is supplied to the low temperature turbine. Superheat can be provided in the low-pressure circuit. Some part of the feed water from the low-pressure zone is transferred to the high-pressure economizer by a booster pump. This economizer heats up the water to its saturation temperature. This saturated water goes through the high-temperature zone of the boiler and is supplied to the high-pressure turbine. Supplementary firing. Supplementary firing may be used in combined cycles, raising exhaust temperatures from 600 degrees Celsius to 800 or even 1000 degrees Celsius. Using supplemental firing will, however, not raise the combined cycle efficiency for most combined cycles. For single boilers, it may raise the efficiency if fired to 700 to 750 degrees Celsius. For multiple boilers, however, supplemental firing is often used to improve peak power production of the unit, or to enable higher steam production to compensate for failure of a second unit. Maximum supplementary firing refers to the maximum fuel that can be fired with the oxygen available in the gas turbine exhaust. The steam cycle is conventional with reheat and regeneration. Hot gas turbine exhaust is used as the combustion air. Regenerative air preheater is not required. A fresh air fan, which makes it possible to operate the steam plant even when the gas turbine is not in operation, increases the availability of the unit. The use of large supplementary firing in combined cycle systems with high gas turbine inlet temperatures causes the efficiency to drop. For this reason, the combined cycle plants with maximum supplementary firing are only of minimal importance today, in comparison to simple combined cycle installations. However, they have two advantages: that is, air coal can be burned in the steam generator as the supplementary fuel. B has very good part load efficiency. The HRSG can be designed with supplementary firing of fuel after the gas turbine in order to increase the quantity or temperature of the steam generated. Without supplementary firing, the efficiency of the combined cycle power plant is higher, but supplementary firing lets the plant respond to fluctuations of electrical load. Supplementary burners are also called duct burners. More fuel is sometimes added to the turbine's exhaust. This is possible because the turbine exhaust gas still contains some oxygen. Temperature limits at the gas turbine inlet force the turbine to use excess air above the optimal stoichiometric ratio to burn the fuel. Often in gas turbine designs, part of the compressed airflow bypasses the burner and is used to cool the turbine blades. Supplementary firing raises the temperature of the exhaust gas from 800 to 900 degrees Celsius. Relatively high flue gas temperature raises the condition of steam, thereby improving the efficiency of steam cycle. Fuel for combined cycle power plants. Combined cycle plants are usually powered by natural gas, although fuel oil, synthesis gas or other fuels can be used. The supplementary fuel may be natural gas, fuel oil, or coal. Biofuels can also be used. Integrated solar combined cycle power stations combine the energy harvested from solar radiation with another fuel to cut fuel costs and environmental impact. Next-generation nuclear power plants are also on the drawing board, which will take advantage of the high-temperature range made available by the Brayton-top cycle, as well as the increase in thermal efficiency offered by Rankine bottoming cycle. The improvement in shale gas extraction has increased natural gas supplies and reserves dramatically. Because of this fact, it is becoming the fuel of choice for an increasing amount of private investors and consumers because it is more versatile than coal or oil and can be used in 90% of energy applications. Chile, which once depended on hydropower for 70% of its electricity supply, is now boosting its gas supplies to reduce reliance on its drought-afflicted hydro dams. Similarly, China is tapping its gas reserves to reduce reliance on coal, which is currently burned to generate 80% of the country's electricity supply, where the extension of a gas pipeline is impractical or cannot be economically justified. specified. How electricity needs in remote areas can be met with small-scale combined cycle plants using renewable fuels. Instead of natural gas, combined cycle plants can be filled with biogas derived from agricultural and forestry waste, which is often readily available in rural areas. Low-grade fuel for turbines. Gas turbines burn mainly natural gas and light oil. Crude oil, residual, and some distillates contain corrosive components and as such require fuel treatment equipment. In addition, ash deposits from these fuels result in gas turbine deratings of up to 15%. They may still be economically attractive fuels, however, particularly in combined cycle plants. Sodium and potassium are removed from residual, crude and heavy distillates by a water washing procedure. A simpler and less expensive purification system will do the same job for light crude and light distillates. A magnesium additive system may also be needed to reduce the corrosive effects if vanadium is present. Fuels requiring such treatment must have a separate fuel treatment plant and a system of accurate fuel monitoring to assure a reliable, low-maintenance operation of gas turbines. Configuration. A single-shaft combined cycle plant comprises a gas turbine and a steam turbine driving a common generator. In a multi-shaft combined cycle plant, each gas turbine and each steam turbine has its own generator. The single-shaft design provides slightly less initial cost and slightly better efficiency than if the gas and steam turbines had their own generators. The multi-shaft design enables two or more gas turbines to operate in conjunction with a single steam turbine, which can be more economical than a number of single-shaft units. The primary disadvantage of single-shaft combined cycle power plants is that the number of steam turbines, condensers and condensate systems, and perhaps the number of cooling towers and circulating water systems, increases to match the number of gas turbines. For a multi-shaft combined cycle power plant, there is only one steam turbine, condenser and the rest of the heat sink. For up to 3 gas turbines, only the size increases. Having only one large steam turbine and heat sink results in low cost because of economies of scale. A larger steam turbine also allows the use of higher pressures and results in a more efficient steam cycle. Thus, the overall plant size and the associated number of gas turbines required have a major impact on whether a single-shaft combined cycle power plant or a multiple-shaft combined cycle power plant is more economical. The combined cycle system includes single-shaft and multi-shaft configurations. The single-shaft system consists of one gas turbine, one steam turbine, one generator and one heat recovery steam generator, with the gas turbine and steam turbine coupled to the single generator in a tandem arrangement on a single shaft. The advantages of the single-shaft arrangement are operating simplicity, smaller footprint, and lower startup cost. Single-shaft arrangements, however, will tend to have less flexibility and equivalent reliability than multi-shaft blocks. Additional operational flexibility is provided with a steam turbine which can be disconnected using a synchro self-shifting clutch. For startup of a simple cycle operation of the gas turbine, multi-shaft systems have one or more gas turbine generators and HRSGs that supply steam through a common header to a separate single steam turbine generator. In terms of overall investment, a multi-shaft system is about 5% higher in costs. Single and multiple pressure non-reheat steam cycles are applied to combined cycle systems equipped with gas turbines having rating point exhaust gas temperatures of approximately 540 degrees Celsius or less. Selection of a single or multiple pressure steam cycle for a specific application is determined by economic evaluation, which considers plant, installed cost, fuel cost and quality, plant duty cycle, and operating and maintenance cost. Multiple pressure reheat steam cycles are applied to combined cycle systems with gas turbines having rating point exhaust gas temperatures of approximately 600 degrees Celsius. The most efficient power generation cycles are those with unfired HRSGs with modular pre-engineered components. These unfired steam cycles are also the lowest in cost. Supplementary fired combined cycle systems are provided for specific application. The primary regions of interest for cogeneration combined cycle systems are those with unfired and supplementary fired steam cycles. These systems provide a wide range of thermal energy to electric power ratio and represent the range of thermal energy capability and power generation covered by the product line for thermal energy and power systems. Efficiency of CCGT plants. To avoid confusion, the efficiency of heat engines and power stations should be stated relative to the higher heating value or lower heating value of the fuel, to include or exclude the heat that can be obtained from condensing the flue gas. It should also be specified whether gross output at the generator terminals and net output at the power station fence is being considered. The LHV figure is not a computation of electricity net energy compared to energy content of fuel input. It is 11% higher than that. The HHV figure is a computation of electricity net energy compared to energy content of fuel input. If the LHV approach were used for some new condensing boilers, the efficiency would calculate to be over 100%. Manufacturers prefer to cite a higher LHV efficiency, e.g., 60% for a new CCGT, but utilities, when calculated how much electricity the plant will generate, divide this by 1.11 to get the real, e.g., 54% HHV efficiency of that CCGT. Coal plant efficiencies are computed on a HHV basis. The difference between HHV and LHV for gas can be estimated by 1055 BTU (pound*W), where W is the pounds of water after combustion per pound of fuel. To convert the HHV of natural gas, which is 23,875 BTU (pound) to an LHV would be 23,875 equals 21,500. Because the efficiency is determined by dividing the energy output by the input, and the input on an LHV basis is smaller than the HHV basis, the overall efficiency on an LHV basis is higher. So, using the ratio 23,875 21,500 equals 1.11, you can convert the HHV to an LHV. So a real best-of-class baseload CCGT efficiency of 54%, as experienced by the utility operating the plant, translates to 60% LHV as the manufacturer's published headline CCGT efficiency. In general, in-service combined cycle efficiencies are over 50% on a lower heating value and gross output basis. Most combined cycle units, especially the larger units, have peak steady-state efficiencies on the LHV basis of 55 to 59%. Research aimed at 1,370 degrees Celsius turbine inlet temperature has led to even more efficient combined cycles, and nearly 60% LHV efficiency has been reached in the combined cycle unit of Bay, a GEH technology gas turbine with with an M3 pressure reheat boiler, utilizing steam from the HRSG to cool the turbine blades. Siemens AG announced in May 2011 to have achieved a 60.75% net efficiency with a 578 MW SGT-5 8000H gas turbine at the Irsching power station. The most recent General Electric 9HA can attain 41.5% simple cycle efficiency and 61.4% in combined cycle mode, with a gas turbine output of 397 to 470 MW and a combined output of 592 MW to 701 MW. Its firing temperature is between 2600 and 2900 degrees Fahrenheit. Its overall pressure ratio is 21.8:1 and is scheduled to be used by Électricité de France in Bouchon. On April 28, 2016, this plant was certified by Guinness World Records as the world's most efficient combined cycle power plant at 62.22%. The Tsubu Electric's Nishiku, Nagoya power plant 405 MW 7HA is expected to have 62% gross combined cycle efficiency. By combining both gas and steam cycles, high input temperatures and low output temperatures can be achieved. The efficiency of the cycles add because they are powered by the same fuel source. So, a combined cycle plant has a thermodynamic cycle that operates between the gas turbine's high firing temperature and the waste heat temperature. For the condensers of the steam cycle, this large range means that the Carnot efficiency of the cycle is high. The actual efficiency, while lower than this, is still higher than that of either plant on its own. The actual efficiency achievable is a complex area. The electric efficiency of a combined cycle power station, if calculated as electric energy produced as a percent of the lower heating value of the fuel consumed, may be as high as 58% when operating new i.e. unaged, and at continuous output, which are ideal conditions. As with single-cycle thermal units, combined cycle units may also deliver low-temperature heat energy for industrial processes, district heating and other uses. This is called cogeneration, and such power plants are often referred to as a combined heat and power plant. Boosting efficiency. The efficiency of CCGT and GT can be boosted by pre-cooling combustion air. This is practiced in hot climates and also has the effect of increasing power output. This is achieved by evaporative cooling of water using a moist matrix placed in front of the turbine, or by using ice storage air conditioning. The latter has the advantage of greater improvements due to the lower temperatures available. Furthermore, ice storage can be used as a means of load control or load shifting, since ice can be made during periods of low power demand and, potentially in the future, the anticipated high availability of other resources such as renewables during certain periods. Integrated gasification combined cycle. An integrated gasification combined cycle, or IGCC, is a power plant using synthesis gas. Syngas can be produced from a number of sources, including coal and biomass. The system utilizes gas and steam turbines, the steam turbine operating off of the heat left over from the gas turbine. This process can raise electricity generation efficiency to around 50%. Integrated solar combined cycle. An integrated solar combined cycle is a hybrid technology in which a solar thermal field is integrated within a combined cycle plant. In ISCC plants, solar energy is used as an auxiliary heat supply, supporting the steam cycle, which results in increased generation capacity or a reduction of fossil fuel use. Thermodynamic benefits of the daily steam turbine startup losses are eliminated. Major factors limiting the load output of a combined cycle power plant are the allowed pressure and temperature transients of the steam turbine and the heat recovery steam generator waiting times to establish required steam chemistry conditions and warm-up times for the balance of plant and the main piping system. Those limitations also influence the fast start-up capability of the gas turbine by requiring waiting times, and waiting gas turbines consume gas. The solar component, if the plant is started after sunshine or before, if we have heat storage, allows us to preheat the steam to the required conditions. That is, the plant is started faster and we consume less gas before achieving operating conditions. Economic benefits of the solar component's costs are 25% to 75% those of a solar energy generating systems plant of the same collector surface. The first such system to come online was the Archimede Solar Power Plant, Italy in 2010, followed by Martin Next Generation Solar Energy Center in Florida, and in 2011 by the Kuraymat ISCC Power Plant in Egypt, Jatst Power Plant in Iran, Hassi Amal in Algeria and Beni Mather in Morocco. Automotive use. Combined cycles have traditionally only been used in large power plants. BMW, however, has proposed that automobiles use exhaust heat to drive steam turbines. This can even be connected to the car or truck's cooling system to save space and weight, but also to provide a condenser in the same location as the radiator and preheating of the water using heat from the engine block. It may be possible to use the piston in a reciprocating engine for both combustion and steam expansion as in the Crower engine. A turbocharged car is also a combined cycle. Bowman of Southampton offer a commercially proven add-on turbocharger which additionally can generate electric power, lowering overall fuel consumption by about 8%. Automotive use. Some versions of the Wright R3350 were produced as turbo-compound engines. 3 turbines driven by exhaust gases, known as power recovery turbines, provided nearly 600 horsepower at takeoff. These turbines added power to the engine crankshaft through bevel gears and fluid couplings. There have been many successful turbo-compound engine designs, particularly for aircraft, but the mechanical complexity and weight are less economical than multi-stage turbine engines. Stirling engines are also a good theoretical fit for this application.